Hey everyone. Today we'll be discussing the hidden engineering challenges behind Ethernet and CAN bus cables. As data demand grows, cable design must evolve to ensure reliability, safety, and long-term performance. We'll break down standard testing for Ethernet and CAN bus cables, as well as the differences between light-duty applications and heavy-duty commercial vehicle applications like truck and bus or agriculture and mining. I'm Richard Trahan, Vice President of Business Development here at Champlain Cable, and I'm excited to share the insights on why specs don't always tell you the full story. Vehicles are becoming computers on wheels. All kinds of systems such as cameras, LiDAR, ADAS, to name a few. These systems require both CAN bus and Ethernet cables to ensure data can be transferred properly. As these systems scale, the infrastructure connecting them becomes critical. Today, we'll explore why cables must be engineered for demanding environments. Cable reliability goes far beyond data sheets and specifications. Commercial vehicle applications can require extremely long lengths at very high temperatures, as well as extremely long cable life. The reason for this is because many commercial vehicles require service life upwards of 30,000 to 40,000 hours. Design decisions made early determine long-term reliability. Our focus today is how engineering choices impact real-world performance. Commercial vehicles face harsher environments than passenger cars. Higher temperatures, longer cable runs, extended service life, and rugged physical conditions. These conditions can expose cables to high temperature oils, automatic transmission fluids, diesel fluids, and a whole host of other harsh oils. Other factors are UV resistance, abrasion, flex life, and general wear and tear in these types of conditions. However, typically in passenger vehicle applications, these environments are a little less drastic and will change the design engineering approach around the cable. CAN bus cables range in size, but typically are 18 to 20 gauge. They're twisted pairs, they can be shielded or non-shielded, and follow SAE requirements. They have a specific characteristic impedance of 120 ohms. SAE specifications ensure the cable is suitable for the application by testing key parameters including abrasion resistance, temperature endurance, hot water exposure, and voltage withstand. Based on polymer science and Arrhenius plot analysis, we can ensure the cable will last for long periods of time. This is essential for long-term reliability to keep brand and customers happy. Ethernet uses similar twisted pair construction, but supports faster data rates. Ethernet is a 100 ohm controlled impedance cable with specific requirements for return loss, insertion loss, LCTL, and LCL. In automotive and commercial vehicle applications, Ethernet uses protocols like 100 base T, 1000 base T, and emerging multi-gig, which can support multi-gig speeds. Standards like SAE and ISO guide bulk cable design. Along with electrical requirements, it's tested similarly to CAN bus for oil resistance, abrasion, hot water exposure, and temperature resistance, to name a few. One thing to note is each cable needs to be tested at temperature. This means while the cable is in the oven for 3,000 hours at its maximum temperature rating, it still must pass all of the required electrical parameters laid out in the specifications. This is required to ensure performance under real thermal load. Commercial vehicle platforms like Class 8 trucks, agriculture equipment, or any application that requires cables up to 40 meters long presents a challenge at higher data rates. At these distances, insertion loss is a critical factor, and the challenges become magnified over the length of the cable. Any imperfection in the manufacturing of the cable can result in a failure and anomaly in the system. Precision manufacturing and advanced insulation systems enable these cables to still perform at 125C at higher speeds over a long length. It's important to understand the temperature requirements, length of the cable, and the data rates needed for the system to function properly. Sustained or peak temperatures of 125 C or even 150 C requires advanced polymer systems. Choosing the correct polymer materials ensures dimensional stability, flexibility, and dielectric consistency over thousands of hours. Using PVC, polypropylene, or other thermoplastic materials can directly affect the life of the cable and consistency of signal. We recommend using high-temperature thermoset materials that can withstand the application for the full service life. Other materials such as the size of the conductor, material of the conductor used, the shielding type, bedding layer type, all influence long-term performance, cost, and weight. Temperature dramatically impacts signal integrity. This is due to copper resistance changes and dielectric shifts. As temperature increases, copper resistance increases. Passing the electrical parameters at room temperature doesn't ensure performance at higher temperatures. This is why governing bodies such as SAE and ISO require testing to be done at the cable's maximum temperature rating. A cable tested at 30 degrees Celsius with little margin relative to the specifications will not hold up at the temperature. Additionally, long cable runs amplify insertion loss. A 40-meter validation at high temperature is exponentially more challenging. EV and hybrid platforms can create harsh EMI environments. This is due to high voltage inverter switching. External noise couples into unshielded twisted pairs, and LCL and LCTL performance is critical with unshielded cables. High-speed data cables are needed for advanced driver assistance systems, or ADAS. Cables become critical component, and any imperfection in the cable could impact a millisecond level response time. Passenger vehicles favor smaller, lighter, cost-effective cables. This is because passenger vehicles, compared to commercial vehicles, have different priorities. Passenger vehicle OEMs are typically looking for higher data rates, smaller conductors, and the lowest cost. ADAS relies on fast, reliable Ethernet cable to connect all types of different systems. Detection, transmission, processing, and response all occur within milliseconds. These cables typically range in speeds, and new platforms have a high-speed backbone that uses gigabit speed Ethernet to support the bandwidth of multiple systems and connections. Sensors and cameras will feed into this backbone with lower speed cables like 100 base or 1000 base. Looking beyond driver assistance systems, Ethernet cable also supports over-the-air updates, warranty data, predictive maintenance, and autonomous systems in commercial and mining vehicles. Mining vehicles typically have the same routes they travel day in and day out and are not on the road with day-to-day drivers. This makes them perfect for autonomous driving. Similarly to mining, trucking and transport vehicles are being reviewed to support autonomous driving across the country, which reduces the need for a driver. No driver means reduced costs, longer road hours, and better efficiencies. These routes are being identified as loops, bringing goods back and forth on a regular basis with the same consistent routes. These autonomous systems require the reliability of high temperature, long-lasting Ethernet cables for the sensors and other equipment. Reliability directly influences uptime and total cost of ownership. Temperature matters. Testing must go beyond the spec for long-term reliability of the cable and systems. Temperature, length, material selection, they're all a true design variable for complex testing and longevity. Above all, The cable is a system component that is critical to vehicle reliability. Thank you for your time. Here at Champlain Cable, we design cables for real-world performance where reliability and product performance are non-negotiable. Please visit our website at www.champcable.com and find out more about our Ethernet cables. Thank you.